The race to build ever larger AI models was based on a flawed premise. A 2022 DeepMind paper just proved that many of the largest, most famous models were fundamentally undertrained. Welcome to our podcast, Artificial Intelligence, Papers and Concepts curated by Dr. Satya Mallick. And as two voices built purely from algorithmic insight, we are, in fact, entirely AI-generated. Today, we're diving into the DeepMind paper, Training Compute Optimal Large Language Models. This is the research that really forced the entire AI industry to rethink its whole approach to scaling.
It's one of the most critical deep dives we've done, I think.
Right.
Because it gets at a really foundational question for LLMs. When you have a massive fixed computational budget, a finite amount of money and time, how do you get the best possible performance?
Right. What's the trade-off?
Exactly. Do you pour all of that into the model size, the number of parameters, which we call N, or do you prioritize the amount of training data, the tokens, which we call D?
And the stakes here are they're huge, right? We're talking about training costs that can run into the tens, maybe even hundreds of millions of dollars.
Oh, absolutely. Wasting that resource on a model that's not optimal, that's a catastrophic failure.
So what was the thinking before this paper?
For years, the industry basically followed the 2020 scaling laws from Kaplan and his colleagues. And their conclusion was, well, it seemed pretty definitive at the time.
Which was?
That performance gains from more data leveled off really quickly. But if you increase the model size, the performance just kept going up and up.
And that gave us the whole bigger is better ethos.
It did. That's how we got a generation of model giants. Look at something like GPT-3, 175 billion parameters, but it was trained on only about 300 billion tokens. The consensus was that data was, well, relatively cheap, but the model size was the real secret sauce.
Okay, let's unpack that a little, because that belief shaped everything for a couple of crucial years. The Kaplan scaling law, it basically put a number on that preference for size over data.
It did, mathematically. It suggested a really unbalanced approach. The law stated that if you increased your total computational budget by, say, 10 times.
A 10x increase, okay.
The optimal move was to increase the model size, N, by 5.5 times, but only increase the training tokens, D, by about 1.8x.
Wow, that is a huge asymmetry.
It is. The idea was to build this enormous neural network and, just assume it would suck all the useful information out of the data set pretty quickly.
So the DeepMind team in 2022 basically just said, hold on, we need to run this experiment again, but much more thoroughly.
Exactly. Their mission was to find the tree function, this L of ND, that models the final loss based on both parameters and data. They needed to map the actual compute optimal frontier, not just extrapolate from old data.
But why over 400 separate models? That seems like a massive undertaking. Couldn't they have just used a few smaller tests?
That's a great question. And it gets to the heart of the problem with the old research. Kaplan's work was mostly extrapolated. DeepMind needed real empirical data points across a huge range of fixed compute budgets. So they trained models from a tiny 70 million parameters all the way up to over 16 billion on data sets from 5 billion tokens to 500 billion. They meticulously carved out where the performance peaked for any given spend.
And the headline conclusion from all that work was a direct challenge to the entire industry.
Yes. In their words, current large language models were significantly undertrained. They were these massive, expensive engines that had simply been starved of fuel.
This podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai. So we've established the old way was flawed, this focus on model size. After running hundreds of models, what was the new answer DeepMind found for optimal scaling?
The answer is actually surprisingly simple, but it was totally game-changing. You need to scale them equally. For compute optimal training, the model size and the number of training tokens should be scaled equally, a one-to-one relationship. If you double the model size, you have to double the training data.
So if we think about it like building a castle, the old way was to build gigantic walls, but only bring in a few cartloads of stone.
That's a fantastic analogy.
And the new way says for every new block you add to the wall, that's a parameter, you also need to bring in more material to polish and detail it. That's the data.
That's it, exactly. They found that if you skimp on the data, all those extra parameters just offer rapidly diminishing returns. And, they proved this rigorously with the math.
Right. Tell us a bit about that proof. How did they confirm this so solidly?
Well, they used 3 different methods, which is key. They look at the minimum loss over the training curves. They plotted what are called isoflop profiles. and they used parametric loss modeling.
And they all pointed to the same thing.
All three. They showed that the scaling coefficients, A for parameters and B for tokens, they both clustered really tightly around 0.50, which, basically just reinforces that equal scaling principle.
We've mentioned the term FLOPs a few times. For anyone new to this, can you just quickly define what an FLOP is here and why it's the ultimate yardstick?
Of course. A FLOP is just a floating point operation. It's the basic unit of work a computer chip does. When we talk about a computational budget, we measure it in, well, trillions and trillions of FLOPs. It's the gold standard for the total energy and time spent. So by fixing the FLOP count, the DeepMind team made sure they were doing a truly fair comparison.
That makes sense. So this brings us to the big prediction. Take DeepMind's own Gopher model, 280 billion parameters, 300 billion tokens. What should it have looked like under this new law?
The prediction was staggering. For the exact same compute budget that Gopher used, the optimal model should have been 4 times smaller.
4 times smaller.
Around 70 billion parameters. But it should have been trained on 4 times more tokens. We're talking around 1.4 trillion tokens, not 300 billion.
So Gopher was just completely out of balance, oversized and underfed?
Drastically. And that means a model like the original GPT-3 at 175 billion parameters on that same 300 billion tokens. It was even more inefficient.
The whole industry was building the wrong shape of model.
They were. The paper projects that for a 175 billion parameter model to be truly optimal, it would have needed to be trained on over 4.2 trillion tokens. That realization was the spark for the ultimate test.
Which leads us straight to Chinchilla. DeepMind didn't just publish the theory, they built the proof.
They had to. So Chinchilla was designed as the real-world test of this one-to-one scaling law. It's a 70 billion parameter model, and they trained it on 1.4 trillion tokens. And here's the crucial part. It used the exact same number of FLOPs, the same total compute budget, as the much larger Gopher.
So it's the head-to-head showdown, same cost, different recipe.
Exactly, the perfect experiment.
And the results, they weren't just a little better, were they?
Not at all. They were overwhelmingly decisive. The smaller, data-rich Chinchilla uniformly and significantly outperformed Gopher across pretty much every single task. And it also blew past the other giants of the time, like GPT-3 and Jurassic 1. It proved that peak performance for a fixed budget came from training a smaller model for much, much longer.
Let's get into some specifics, because this is where it gets really impressive. The MMLU benchmark, massive multitask language understanding, that's a tough one.
It is. It's a huge battery of tests on general knowledge. And on NMLU, Chinchilla hit a state-of-the-art accuracy of 67.6%.
And Gopher?
Gopher was at 60.0%. That 7.6 percentage point gain is just astronomical in this field, especially since they cost the exact same to create.
And that 67.6% wasn't just a win, it was a leap forward. It actually beat the expert forecast for what state-of-the-art would look like 6 months later.
It really did. It showed the potential was far greater than we understood, and we saw this everywhere. On reading comprehension tests, RACE and RACE-EM, Chinchilla improved accuracy by over 10% compared to Gopher. Better scaling directly led to better reasoning.
Now, for the people listening who are on the deployment side, the engineers, the practical win here is maybe even bigger than the performance bump itself.
I completely agree. Think about it. Chinchilla is 4 times smaller than Gopher. That means substantially lower compute costs for everything you do after pre-training.
Like fine-tuning and inference.
Exactly. Fine-tuning, serving the model, all of it. You get a better model that costs a fraction to actually run. Suddenly, the best model for that budget is also way more accessible and easier to deploy.
It really lowered the barrier to entry, but was it only the scaling? Were there any other little architectural tweaks that helped Chinchilla?
That's a fair question. The parameter data trade-off was the main event, for sure. But the team did note a few minor improvements. For instance, they used the Atom W optimizer instead of plain Atom, which gave a slightly better final loss, and they had a modified tokenizer. But these were really marginal gains compared to the massive benefit from the compute optimal scaling.
Okay, so shifting gears a bit, DeepMind also looked at the ethical profile of Chinchilla versus Gopher, since they shared the same training data.
Yes, that was a really necessary step. The question was, does making a model smarter in this way unintentionally amplify risks like toxicity or bias?
And what did they find on toxicity?
Well, they generated about 25,000 unprompted samples from both models and checked them. And what it showed was that the toxicity levels were largely flat. The mean score for Gopher was 0.081 and for Chinchilla 0.087.
So not a significant difference.
Right. It suggests that just improving the core language modeling quality doesn't automatically make the model more toxic. It seems to be somewhat independent, at least in this context.
But on specific biases, like gender bias, there was a more encouraging story, right? On the Winogender dataset.
That's right. That data set tests how well a model resolves pronouns when gender stereotypes could interfere. Chinchilla was more accurate across the board compared to Gopher. The biggest jumps were for female and neutral pronouns, up by 8.3% and 9.2%. And on the really tricky gotcha examples, the ones that specifically contradict stereotype, performance improved by 10%.
So making the model smarter and more efficient also made it a little bit better at overcoming some of the biases in its own training data. That's a fascinating side effect.
It is. It suggests that a properly trained, compute-optimal model is just more robust in general, even in sensitive areas.
So let's wrap this all up with the big takeaway for the industry. If the whole bigger is better race was the wrong path, where does the focus have to go now?
The focus has to shift fundamentally, away from just model size optimization and toward dataset scaling and high-quality data curation. This deep dive proves that the bottleneck right now isn't the model architecture. It's the volume and, just as importantly, the quality of the data we feed it.
And the numbers they project for the future are, well, they're sobering.
They really are. If you extrapolate this new one-to-one scaling law to a hypothetical 1 trillion parameter model, which is where the field is heading, the paper projects you'd need an astonishing 21.2 trillion tokens of high-quality training data.
21 trillion. That is orders of magnitude more than what we were using just a few years ago. The challenge is no longer just building the model, it's finding and cleaning all that data.
It changes the game entirely. Future breakthroughs will rely on superior data sourcing and filtering, not just on ordering bigger and bigger chips. This paper showed we were building these incredible engines, but we just weren't giving them enough fuel to see what they could really do. And as a final thought for you to consider, this whole study was done on autoregressive language models. But this principle of trading off parameters and data for compute-optimal performance, it's almost certainly applicable across all large-scale foundation models. So whether you're building for vision, for multimodal, or for science, finding that sweet spot between size and data is now the essential first step for anyone training a model.
If you are looking to understand the fundamentals of computer vision and AI that make these incredible models possible, we urge you to enroll in opencv.org University to get started in computer vision and AI. That's it for this deep dive into the paper that changed LLM scaling forever. It proved that efficiency, not just massive scale, is the key to unlocking true AI performance. Thank you for tuning in, and be sure to subscribe to the deep dive for more concise and insightful knowledge shortcuts.